So welcome again to our Mechanical Engineering Research Seminar. Today's speaker is Dr. Hadi Fekrmandi, and he's going to talk about autonomous agents and an interesting application for lunar exploration. So welcome.
Yeah.
Thank you. I could close this for you.
Hi, everybody, and welcome to the ME seminar series. Thanks, Micah. I am going to today be presenting the multi-agent autonomous guidance and navigation and control using SVGS sensor for lunar surface mobility applications. Very long topic, but generally autonomous GNC multi-agent systems. So what I'm going to be in general presenting has the outline of the following. I'm going to be talking a little bit about the background, a very interesting background that NASA has been working on towards this point and what they are planning. And then objectives that we had, particularly in the research that I did during the summer at Marshall Space Flight Center. And then I'm going to also be describing the problem that we had and we tried to address as a research problem. And finally, the method that were used and the results obtained. And part of our future plans is experimental validation and verification that we are addressing. And we are working on currently over the state and over the collaborators. Okay. So we all know NASA is planning sending the rover to hunt for the water on the moon. So generally, NASA's plan over the next, this upcoming decade, 20s, is to send astronauts, robots, stationary rovers, and also orbiting gateways around the surface of the moon. And the whole idea has the objective of going to the moon for basically finding the resources. So why moon? Why not first Mars? So if you think about it, the reason we are trying, the NASA is thinking about this idea is moon has been discovered with the subsurface water resources, and this is more of a technology demonstration. The idea is to be sure that we are capable of doing something that is like in a matter of couple of days away from us in the space before taking it to the next level on the Mars planet that is a 2-year journey. So that's the primary mission, basically create or at least demonstrate a sustainable human presence for the Mars. And then this would be feasible through exploration and exploiting the resources. This is the goal. And the Artemis is the program that NASA is currently has about going back to the moon. And the Artemis program is basically the program that we know that is, if you see in the corner, it shows the Mars, and going basically outline is to go to the moon as a gateway to the Mars, and the whole idea is to have this astronauts, rovers, and multiple missions. But the primary objective is what you can see is to have the mobility system and mobility rovers, and also the stationary stations and also astronauts to be presenting on the moon. All right, so a little bit about the history of what is the background. LCROSS was the Lunar Crater Observation Sensing Satellite. This was the first in the 90s that the scientists and engineers in NASA started thinking about moon is not as dry as we thought that it is. It seems that moon is wet. And then immediately in 2 years, NASA Ames Center led the effort. And in 2 years, there was a mission called the LCRS, standing for Lunar Crater Observation and Sensing Satellite. So the objective of here was to send basically a rocket crash to the moon and immediately pass by around and probe the dust that has been in the shadow for a long time, and evaluate the content of what is inside. And very quickly, in a matter of from June 18, that this was in 2009, this was launched along with a lunar reconnaissance orbiter. So that was a satellite that stayed in the orbit, and these two the vehicles, the space vehicles, conducted the mission. The results show that very promising. Permanently shadowed areas in the southern pole of the moon were hosting significant, or at least visible, amount of water and other minerals. And also on 2009, the same year, NASA announced that confirmed the discovery of the water on the moon, on the lunar, based on the results obtained from this impact. The history of the rovers that has been to the space, not just the moon, but the Mars and moon overall, the rovers, there have been autonomous rovers like Curiosity, the most recent one, the Perseverance, that 2020 was just it was launched. We also have the Apollo 15 lunar that was in the early days, that was driven by the astronauts, and a range of vehicles have been deployed so far, including the Long-Hod 2 lunar rover from the Soviet Union that hold the longest rover mission on the surface of the moon for the longest, for almost 30 years. It covered about 26 kilometers, I'm sorry, 26 miles. The most recent versions include Mars Exploration Rover, MER, as well as Sojourner on the Mars. And also we have Chinese rover that is, there's the two versions, U2-1 and U2-2, which is the Chang 4 mission that they are ongoing, and they are actually doing some very interesting probing from the moon. If you look at the moon, if the slide is clear here, if it shows most of the moon missions that has been conducted so far, I mean, they are around the equator and also in this area, and that includes even the most recent Chinese mission, U2-1 and U2-2, and then also the distance of each rover is covering is shown. As of now, most of, or every mission that has been conducted has been limited to single rover missions, and there is so much that can be done when it comes to the exploration, when it comes to the other ambitious plans that the NASA has, like create a station for astronauts, permanent, sustainable, rather than few days or few hours that has been done in the Apollo mission. That requires a different level of investment, but this is what the Chinese Chang 4 lander and the U2 rover have learned and find out by the new instrument that is on the rover. It includes a ground penetrating radar that showed the 3-layer, basically the fine soil for the first 12 meters, and then there's a coarser rock boulders embedded about 12 meters below that point, and then an additional sub-layers of coarse and fine combination for up to 40 meters, and no one knows what is below that. But again, this is one rover trying to cover one trajectory, and that is basically what it is showing. It is really promising, and these results are showing that it is possible that doing the exploration in a polar point of the moon would give much more interesting results. So the Viper is the mission. Actually, Viper, if you were following the news, you might have seen that the Viper rover was awarded to Astrobotics. But based on my knowledge, Viper has been like a development of the rover for the moon that has been going on the like NASA, led by, interestingly, by Science Mission Directorate of NASA headquarters, and it is part of the supporting of the Artemis program. Actually, the robots, one of the ideas is the robots are going to be going before the astronauts and be sure that there's a level of preparation. And if you look at the Viper rover, everywhere you're going to see this rover, that is the moon rover that is being developed. It has like a LED brightening in front of it. The reason for that is the areas, there are areas in the south pole of the moon. In this video, you can see that they're permanently shadowed. And that's why they have a much likelihood of having water, like in more accessible layers in the south pole. So this rover is actually being constructed at this point. It is under development, and it is planned well, one of the interesting things is that makes me think that there is a possibility of having multi-robot missions, is the fact that the developments that have been done on the rocket technology, the new SLS system or the Orion are capable, and along with the SLS, along with the gateway in the moon orbit, are capable of basically handling many, more cargo deliveries than what it is. So like this video, as it shows that we are trying to get to the Mars, but challenges are just too many to go directly. And another rover background again shows the Mars 2020, like the Perseverance. And if you look at the sensors on the Perseverance, I don't know if they can see my mouse, the nav cam are the two front cameras. There's front has cams and then back has cams. Those are cameras to see front and back. And then there's also the navigation cameras. I mean, there was another video that I really wanted everybody to see, and that was the part that, especially the very short part that Elon Musk is talking about why vision is the way to go when it comes to autonomous systems compared to laser LiDAR system. We as biological creatures, we don't shoot laser from our eyes to measure the distance. We just the brain does that very, like, it doesn't feel for us, but it's a very interesting process. And this rover, this particular Mars 2020 has autonomous capabilities. So it can go like segments autonomously based on the onboard calculations. But even that being said, between the two, it does the dead reckoning. That's when it uses the odometry of motors to estimate where it is located. And there has been research in a couple of NASA centers that shows that this positioning of the rover actually, I mean, there's a slide that happens. If you see, follow the Curiosity, the wheels are almost ripped off because of the terrain, and those also slips are happening, and it is very hard to have a localization of the robot. That same process that Soviet Union rover had, there was a discussion between the Soviets and the NASA scientists in terms of what was the length of the actual distance that the rover has gone, because they had the data from odometry that shows the wheel rotation, and that was not matching to the data that is coming from vision or from the orbiter showing the lunar reconnaissance. So that was in the order of like 1/10 of a kilometer, and that's too much if you want to do anything more accurate. So one of the interesting things that this rover is going to do is to take samples and just leave the samples on the ground of the Mars for another future mission for them to be picked up, because of the fact that, you know, if we want to look at the history of the Mars, it has to be something really, really, you know, it has to be done on the Earth science labs. That's not something that we can do on a rover lab. So the samples need to come back. But in general, I just wanted to mention about the navigation capabilities that is here, but that is also very limited. So our mission was the research that I conducted, and you know, starting from the background of the multi-agent systems, the project that initially in 2018 was supported by Office of EPSCoR at South Dakota Mines, and this was an opportunity for us to learn about the multi-agent system. So here, we had with this project, we have the goal of autonomous guidance, navigation, and control, or GNNC. Anywhere I'm using GNNC, that's what it means, using the smartphone video guidance camera sensor. So SVGS is the camera sensor that has been developed as a low-cost sensor for vision sensor that is capable of state estimation. That means that it can give you like the position, orientation, velocities. Ideal scenario is when is to complete the mission task and by grabbing the samples and, you know, coming back, navigating using the SVGS. But there is also challenges on that. Every time SVGS has been used, this has been developed by the NASA Marshall Space Flight Center. It uses LEDs, and this block that you see here is like a CubeSat, 3U CubeSat, that has these 3 LEDs, and those LEDs, along with one off plane with the 4, so it creates like a diamond shape here. They can be used for some as target, and this sort of target is like the camera, or the smartphone camera, and the reason for a smartphone is just like an Android, very low cost smartphone camera, can take an image, filter it, as you see here in the picture. It can be taken in the picture that has the arrows that follows. That can be filtered and associated with the data. And if we know what was the original size of the target, that it's possible, based on the geometric relationship, obtain the camera point of view, XYZ and roll gap pitch. But the SVGS had its own journey. It went from retroreflectors, which is shown in the target options, to the LEDs at targets that were more reliable and created less noise and reflections, as you see in the right corner of the image, and then, like, going from the left 6 are from the retroreflectors, the right 6 are from the LEDs, and that's pretty reliable when it comes to this sort of state estimation that has been done by SVGS. But every time SVGS has been used has been for very short distances. Here you can see, of course, the targets were very small. So the idea is, I mean, the targets are installed somewhere, and that target becomes like a measurable order. But then you see the issues here. There is the challenges of 12 meter and above. 12 meter and above, there is some basically bleeding of the colors. And then we also have LED image that is on the right-hand side. That's called in the dark room. Anything beyond 3 to 5 to 6, 10 meters, it creates these issues here and go. They have been addressed by much better camera smartphones. This was 2013 initially camera. Now we know in in this decade, it has been significant process. But even the only application that I have seen, it has most recently it has been used on a rover for some navigation and docking. So I'll need some water, excuse me. And feel free if you have any questions to ask. So what happens here is that the motivation that we had is that in ideal condition, SVGS has shown very promising. So this table shows that the first 3 rows versus the first 4, actually, the ones that shows operating range. This operating range is the operating range is, if it is 0 to 3 meter, then it has like a 3 sigma error of depth estimation of 0.2. That means 2 centimeters for the first 3 meters. That actually is really good. And then up to 30 meters with 0.747, that's like half meter up to 30 meter depths, like the distance of the error, and also the same type of error that has been shown for X and Y. So these data are measured and collected by NASA Marshall in a very good condition, obviously, based on what I see. And they have also been repeated for another target. That target is LRT. We have SRT and then the LRT. Obviously, LRT is the long range targets, and they are just larger and brighter LEDs in a way that they can be seen from further away up to 300 meters. And this means that you can install these targets in the robots, and then the other robot can look at from its camera to this one and use the SVGS algorithm, which I didn't explain it, by the way, but that uses the collinearity equations and minimum. It has also a little bit more than what you see in typical OpenCV codes. It gives a good result in terms of error estimation. So it gives a state estimation of the target that the camera is taking an image. So if these images are repeated, that's going to be like creating a video, and you can have a stream of the state and kind of do the same thing that perhaps a LiDAR can do ideally with a vision, and vision has all these benefits. It is low cost, low power. If you look, the robot that is being developed, the rover, it does, like the Viper rover, it already comes with a camera, definitely, and also it has the LEDs for brightening. I don't see any issue if that can have 2 additional LEDs, and obviously I don't see how it might be, but it's very, very easy to equip an additional sensor that gives you a relative motion of a mobile robot. And that's very valuable if you consider that how much like that the Russian scientists had issue about of state estimation, and how important it is to know where you are in that darkness. And now it is dark, that area in the South Pole, there's permanent darkness, and there's areas that have very little to no sun. This state estimation is very valuable. And also we don't have a GPS system. So this is a research that has been also in one way has been addressed using the Aruco tags or AR tags that are installed. This shows 2 Ross rovers here at the EEP building, developed by the research group of Dr. Hoover, and they are doing a leapfrogging motion. The figure in the below that has ABC, that shows the leapfrogging motion that that one robot is localizer and the other robot is follower. So one has the target and one has the camera, and basically it sees the target, it makes an estimation of that, and then it allows it to move. And then let's say it moves to the second position, and this guy follows it and gets close to it, then makes another estimation, because the closer you are, the better accuracy of the estimation. And this way, it can create, well, here it has been used. In the next slide, you can see that this technique has been called CLAM because it is doing the SLAM, which is the simultaneous mapping and localization using the RGBD, or using the depth camera. It has used it for mapping this the corridor. I don't know why the slides are just going on their own. They just change quickly. So that's, I'm sorry about this. It's a complete technical issue, but I'm sorry from everybody. I'm trying not to touch it, but it changes. So once you look at the image here, you can see that the map that is generated, if you see where it is starting in the corner and it is going, their error accumulation is visible. The map is kind of deviating from the corridor. It is very accurate, but as you continue, this only relative state estimation, it is adding up. It is adding. So if there was slipping because there was sandy area, that was an error was coming from the locomotion. That would be also added to this. But still, it is very, very helpful, and this is very useful. But there's a challenge with this use of relative state estimation and vision, that one robot is gonna be like needed as a follower for the target robot to give estimation of that robot to itself. And also, basically, how do you know that the robot that is following, that one is also occurs slippage or error? So it is a little bit difficult when it wants to go to the space applications. And the method that I have been working on is basically on the concept of robotic, the probabilistic robotic. You can see probabilistic robotic is the area of the robotics that is growing very fast. There's a significant amount of interest in it because of the fact that this probabilistic robotic has the opportunity of letting our robots to have some uncertainty involved. It's okay if you have some slippage on the sand. In the right photo, right image on the part B, you can see that the two trajectories, one is the actual trajectory and the second one is perception of the robot, where I think I am as a perception, because like, how do you know where you are if you just only measuring your wheel rotation? That's odometry or dead reckoning. If you are making estimation with some features, you see that the trajectory on the right hand side is close to these features on the environment, then the error is okay. But then if it is further away on the picture and then on the left hand side, this perception of the robot deviates from where actually it is, and that's where we have the problem of lost robot. And that can happen, the same thing that happened to the Soviet robot, it can happen here. But if we want to do something meaningful that's really localized where robot is, where have accurate data from the samples, then that is not really acceptable. So we want to make sure that our robot does have uncertainty, but can handle it. How is gonna happen? Well, here I have some slides about the vision, that technique that we have done. This is the EPSCoR RIG grant that was funded. There's the part of it was vision. We wanted to offer an alternative for the SVGS that is being used. That SVGS has the issue of it's not capable of giving a data association. So the SVGS cannot do that, but the ARUCO tags, they can. And we showed that they are also reliable, but even our data shows that, I mean, up to the 3 meter, it's not really showing anything beyond that. But these are just very small little cubes. Cubes are 10 by 10 by 10 centimeters. So definitely there is a lot that can be done to improve this measurements. And we have done in the second results to sub-millimeters by just simple calibration. Not sub-millimeter, but it is in the range of less than 1 centimeter. Those are once you deduct the average error as a calibration. And So then because the background, we were working, there was some work that has been done on developing the Earth planet, like the low Earth orbit dynamics that we have done. But the core of this research was to focus on creating some multi-robot guidance, navigation, and control. And this means that the multi-robot guidance, navigation, and control means that we have more than two robots. We want to have a technique that robots are making relative measurement and they are able to recover their global state. You know, relative to each other, we can have any orientation and any distance, but then where is actually we are located? So this is where things get interesting, and recently we worked on a technique that is called distributed state estimation that allows to it is scalable. It can go beyond more than just two robots or three robots. Here we are showing three robots, and the data can come from any resource. It doesn't have to be coming only from vision, obviously. But the thing is that how do I have multiple? Like that's if we have more than two or three robots, and also there is a possibility of link failure. So the probabilistic robotics in general is a technique that we chose, but in that context, the distributed state estimation is used. Here in this slide, you can see the robot environment, robot sensing. These are the sources of the uncertainties. It's even if it is not sandy environment, it can this can come from a lot of different resources. The uncertainty. So sorry. Michael, are you sure that you're not touching anything? This is switched on. Okay. All right, so let's go to the next slide. So the proposed method, I have talked about it. It's use the probabilistic algorithm, particularly the distributed state estimation, and use also the SVGS sensor, because I mean, that particular sensor is important for NASA. They have been developing, and as we saw even in the commercial side, Elon Musk is pointing that direction. Go vision, not other things. And we know that it is the right way to go, and the vision has many things. It is being used with the rovers for the distributed state for relative state estimation, and then we also wanted a technique that is more scalable to a higher level. And here I have the Z, the filtering is the process that recursively we are trying to compute the posterior probability of a random dynamic process in a sequence measurement. So if our ZK, K indexes for time measurements, if ZK indexes are Z1 to ZK, and these indexes show that you have K different measurements over the time. So that's where the filtering comes to the play. I am moving, at the same time I'm making measurements. So there's a prediction from where I'm going based on the transition model as a robot. And then at the same time, I also make measurements simultaneously. And then the filtering allows this to combine this data, prediction and a measurement, and then have a better estimation. Reduce the uncertainty, which we showed with this ellipsoids of showing the uncertainty covariance. So the and then why decentralized? There is, as I mentioned, scalability, modularity, and robustness. These are the reasons that we want to have each robot making their own measurement, and regardless of who they are seeing, if they are seeing everybody or they are just seeing multiple of their neighbors, still be able to recover a global state of themselves. And basically that's why when something is centralized, that means that everybody sends their measurement to a central node, and that one does the calculation based on the relative measurements, and then calculates who is standing where based on their state, velocity, orientation, direction, and then communicating back to the original. But this is too ideal. It's not always feasible. As we saw in the moon, if the distances, let's say in the vision, if the distances are increasing, immediately we're gonna have this issue of error increasing, and then the link failure can happen. Like the error is just too much to be reliable. Same thing on the other hazardous environment. Under sea, we have sonar relative measurements. We can have a lot of reflections that are not real, misdetections, false detections, like there's something that you're not detecting, or there's nothing and you're still detecting, and all of those issues in other environments. As we saw, we want a technique that is able to handle that uncertainty coming from everywhere. The motion, and then we wanted to, in the context of the robotics. So the motion model is here, the very simple motion model. It's called the unicycle robot model. That has a model of the robot that X is the state and F is the transition model. And then we also have components that are related to noise and the input from the motors. So this predicts next step in the time versus what I'm going and what I am measuring. And also based on the omega. Omega is the almost constant velocity assumptions that we have. But here, what is interesting is that we do have some uncertainty involved, and that's like the Gaussian noise with the mean of 0 and the covariance of the Q. So this is like the most simplest possible robot transition model that we consider, but it still is nonlinear, and it still allows to include the nonlinearity and the error. And the error, we defined it based on the SVGS data. So we defined the observation model that was showing based on the measurement coming from the SVGS system, and the error table that we had for the first 30 meters, it was a reasonable error, and we wanted to use that in a model. Given that during the summer we didn't have access to any experimentation or any lab access, we wanted to use that as our observation model, which here is shown as H. That makes the measurement Z. So network topology is when, as I mentioned, each agent in this network can have relative measurements, and then they also can have disconnections as well. But then the way that the distributed state estimation works is that the system, it is very similar to like the information that is communicated between the two are very effective. So here we have delta I, like lowercase r, and then the capital I, let's say from the agent R1, and then they are being communicated to the other agent, and then also they measured it from here. That means that if I am any agent, depending on how many connections that I have to my neighbors, each of them, they're gonna give me something. Okay, this is your state. And then I'm looking at the other side, I'm looking, say, there's another state coming from. So how do I make this consensus over multiple measurements, and then also some prediction based on my own model of the transition, which was the robot unicycle model. So the distributed state estimation does that by using information vector and information matrix. Information matrix and vector, everybody is familiar for the most part with the Kalman filter, and how the Kalman filter or extended Kalman filter can be used for making measurements, for making basically fusion of the measurement and the prediction. Information filter, you can easily find it. It's like the evil twin of the Kalman filter. Instead of using here you can see instead of using the information vector is the inverse of the covariance, and then information matrix is the inverse of the covariance, and information vector is inverse of the state. And that's how, I mean, the first equation is the information vector, that inverse of the covariance multiplied with the state, and that's the lowercase y, and then the capital Y is the information matrix. So here we have the basics that it is going to be used. And what is interesting in this information representation is that when you want to do the fusion in the second set of two equations, you can see that the prior is always in the probabilistic methods. There's like a posterior, and then there's like the prior, and there's the update. And the update here is only just summing the informations that are coming. You see J1 equal to capital N. N capital N shows the like number of the nodes that each agent is communicating in. And that's as easy as just adding these informations. There's nothing needs to be done compared to the Kalman filter that there's multiple matrices need to be calculated. So it makes it very easy for communication. Is very helpful. And how much time?
So you have about 10 minutes left. It looks like you have results and future work. So
yes, yes.
Fit all that in. And then some of the slides seem to be set for advance automatically after 20 seconds, but not all of them. So I don't know what happened there, but apologies for that.
Okay, yeah, I am also, I'm apologizing from the audience if this has been uncomfortable. I have seen that before in there's some very back. All right, so decentralized estimation. Well, basically the distributed state estimation is using a hybrid of the two different techniques that are established, and that has been showing that it makes a significant improvement based on this prediction for the fusion of the data coming from multiple nodes. One is the MHMC, the method that is here is shown. It has a formula, like these weights are calculated depending on how many nodes you are communicating, and then is multiplied with the information coming from there, and then summed. That's the law of fusion used with the MHMC. And then there's iterative conservative covariance intersection, and that's a more conservative way, and it uses some optimized omega star weights of the incoming information from other agents to fuse them. And we have worked on developing a hybrid method, and that's how we have done this. So the results show that the experiment that we did, I mean, it was in MATLAB. We used a platform called OpenMAS. It's in MATLAB, but we are moving on from MATLAB. We are going to the ROS to allow us to be able to test and experiment in experimental testing, because that's NASA is about there. They just don't want to see only beautiful formulas. And the good thing is that we want to make sure that it works. So if you look at this, three agents are starting from 0, 0. One goes to the up to 40 meter away, 30, 20. No, 20 meters away to the first waypoint, and one just goes directly, and then the other one comes to the down. Okay, so this is the trajectory, and then they make the turn and they go back to another waypoint. The waypoints are shown by the diamonds, and then what we have here is that decentralized means that every agent makes estimation of everybody in the system, regardless of if it gets the information from them or not. So the first set of equation is that where we are not using consensus, we are not using the hybrid consensus used in the distributed state estimation. And you can see, let's say, for the trajectory on the most left picture image, you can see there is there's three graphs. One of them is the blue that is really like nice, but then the other ones are the error increasing, because the other ones are the estimations of the other robots from this trajectory, right? So there was one that was going straight, there was one that was going down and then making turn. So the one that was going on the other opposite direction and then making turn, that was the one that had the highest distance, and that shows the yellow. That, I mean, it has some error. And those ellipses that you are seeing, those are covariances. Obviously, covariances are also increasing. That shows the area of uncertainty. We know that robot is somewhere around there. And this is when we don't use we just use simple Kalman filter. And then we also did the consensus with the hybrid technique. And the hybrid technique was able to, as you see, even all three of them on the most left picture. And same thing for the other two robots. Like every robot has three estimations. One is by itself, and the other one is by the other two where it is. And as you see here, it is these estimations are much more better. I have another picture that are comparing them side to side. You can see for the robot going to the first trajectory to the above, and then the one that goes direct, and the one that goes on the opposite direction to the low, and then makes turn. Both, on all three cases we have seen improvements, and then we have seen also improvements. These are covariance. Covariances, and covariances are uncertainty. Covariance always increases no matter what, but still we have seen improvements on that as well, and still ongoing the research. So the future work is, as I said, NASA wants to see the actual experimentation. So that's what we are moving very quickly to Python, and then from there to robot operating system, thanks to some of the students that I have with the backgrounds that they have. This is going to somehow smooth. So we are planning to actually use, now that we have the access to the facility here, thanks to ME, we are building the SVGS, 3D printing, assembling the LEDs, and we are going full force on making our own version of the SVGS and compare it with our vision sensor. And we also are going to implement the DSE on the robot operating system with the turtle bots that are pretty reliable, low cost, and then there's a whole community that is supporting you. If you get stuck, there's going to be somewhere to get out. And this is the good thing about it. But then what is the future work, like future? This is what we are doing actually right now. Future work in terms of longer term for the major grant is to look at the actual environment. So NASA aims in the same robot operating system has developed an environment that is for, that environment is for moon environment that resembles the dust, the uncertainty. We want to take the robots, implement in that simulation gazebo environment, and then validate the DSE as well as when the data is coming from the SVGS, and show that we can go beyond the state estimation. The other side of this game of multi-systems, multi-agent system is control and exploration. And that's the side that is led by the South Dakota State, SDSU. And as far as I know, there's also very good news always coming from there. And we have been able to use this state estimation. Once you have a good state estimation of the swarm and then the members in the swarm, then it is much, much more reliable if you want to implement some exploration algorithm, for which we are looking at the deep learning and improving, actually using the SVGS targets in the background of the image in a way that reduces the computational cost and improves the overall state estimation for exploration. That's what NASA is planning to do. They want to explore, and they want the robots not to get lost. And because we are having this capability of multiple delivery, hopefully one day it's gonna get there. So basically that's the future plans. And in short term, these are some experimentations that have been done, but they are not relative robot to each other. They're just relative to a stationary target. But the first target is further away. It's a Aruco tag. This is not SVGS still. Obviously, we have been during the RIG, we have been mostly working on the on the Aruco tags that are also pretty reliable. But SVGS, in a way, when I'm thinking honestly, I think SVGS is better, because in that darkness, you just need 4 LEDs, and they're gonna be seen for very long distance. The Aruco tags, I think they can also work in a combination to each other. Basically, for very short distances, Aruco tags are also, they also solve the association problem. But for longer distances, I think SVGS can be offering NASA a significant improvement by robotic guidance navigation. It should not be just limited to think as for docking that has been used before originally. So it can be, if you use it with the right algorithm, we're gonna have that. And the other thing that we are looking also is that in that shadowed area of the moon, batteries are very important. We have also a new member in the team that we want to make a global optimization of trajectory that is going to be planned between each robot for optimization. And there is data that research that I was studying that multi-robot versus one robot is it's orders of the magnitude difference when you want to do a discovery. And that's like targeted discovery. You make a sample and then based on that, you change yours. So that's a lot of things are upcoming. Obviously, there's research and it's a collaborative team. And I really want to appreciate everybody that has helped, including NASA, Marshall Space Flight Center, and Mr. Rakosi and his team at Division EB41 during this summer. And since the time that I get connected to them, thanks to Dr. Larshell, that we made the initial connection. And since then, we have been working very effectively. And again, thanks to also Dr. Duke from the South Dakota NASA EPSCoR program. This was a great 2 year that we had, and we are on full thrust, hopefully, to continue this statewide collaboration and extend it to the next level with AIMS and JPL are coming on board. I also am grateful from the Office of Sponsored Program here at the South Dakota School of Mines. And then everyone, the students, especially the School of Mines, the students, most of the work that you see, that's the students that are doing. Sky Rutan Bedard, Alex Fry, Joseph, and Amir Tamjidi, my friend from Zoox, Autonomous Driving Cars. He has been taking the time working to this Silicon Valley type of work and still help us. Dr. Hoover, Dr. Kyle Riley, and Dr. Kyle Cottle, and a lot of other faculty in the School of Mines, as well as SDSU, Dr. Vaughn, and the Naval Warfare Center that recently they have also started looking at and supporting our effort in this topic. So thanks everybody, and also thanks students, Dr. Ash, everyone.
Great.
If any questions, I'm sorry, it took too long,
Yeah.
and sorry again for the jumping of the slides, which was unexpected.
So let's give Hadi a round of applause. We're out of time. Next week we have speaker, Dr. Wendy Zhu from Cornell Tech. She'll talk about autonomous vehicles, but it's about cars and on Earth. So join us for that.
It's a